Okay, well, welcome everybody to the next installment of our online paper reading group. Really excited today to be welcoming Professor Zhangyang Wang. He is a tenured professor, tenured associate professor, and holds the Temple Foundation Endowed Faculty Fellowship number 7 in the Chandra Family Department of Electrical and Computer Engineering at the University of Texas, Austin. Meanwhile, in a part-time role, he also serves as the Director of AI Research and Technology for PixArt, where he leads the development of cutting-edge Gen AI-powered tools for creative visual editing. He has a broad research interest spanning from theory to the application aspects of machine learning. He's currently, at present, his main research mission is to leverage, understand, and expand the role of sparsity from classical optimization to modern neural networks. The impact here spans many different topics, such as efficient training, inference, and transfer, especially of large foundation models, robustness and trustworthiness, learning to optimize, generative AI, and graph learning. So you might have noticed I was reading that. But yeah, really, really great to have you with us. Really excited to go through this paper. Yeah, the floor is yours, Atlas.
Thank you so much. And thank you for having me here. I'm really excited today to share our research on a topic of sparsity, which is really close to my heart. So let's start from some house cleaning. First, since I hope everybody here is agreeing on, today's AI is too huge and we want to make it smaller, right? So when we work on AI models, we know what expensive means. And there are many ways to develop since the very beginning of deep neural networks to making AI cheaper in the realm of model compression. Well, there are two main streams of method in model compression primarily, quantization and sparsity. Both are effective and often they are used together. So today we're mainly talking about the sparsity, which has been a popular option for compressing AI models. So sparsity also have a lot of meanings. Well, for example, sparsity, originating from the old philosophy of Occam's razon, sparsity has been leveraged at every aspect of model simplification. For example, you could pruning the weight, you could pruning the activation, you could skip a part of the model, or you could dynamically choose a different submodel compute, including the reason, the fame, the mixture of expert. Sparsity really have many different means. And I'm taking this figure from a very nice paper, GMR 2021, called Sparsity in Deep Learning, where they have nicely summarized all the possible forms of sparsity on model level or activation level and the different structures, different weights and neuron parts. And it's just incredibly rich. And today, I will only talk about a very small part of sparsity. I will focus on the weights. And for the most part of the talk, I will be talking about the unstructured weight pruning, which is the most basic form of sparsity for model compression. There is a reason I love that. I love this aspect, and I will try to defend my choice later. I will discuss the key research question that arising our curiosity and where the focus of today's discussion is. Let's talk about the pruning, unstructured pruning primarily, and weight pruning. So as our model getting bigger and bigger, is pruning a larger model easier or harder compared to the normal range of model sizes that we're familiar with? Normal range here means probably where this literature has been published the most, the ResNet or VIT, we call it the sub-billion level. So a ResNet is 200, anywhere between 200 and 700 megabit parameters, and the VIT is sometimes larger, but usually we call them sub-billion level or just a billion level. But when we come to the large language model, which can reach 10 billion level or even larger, would the sparsity becoming more effective or there will be more tricky to utilize? So I want to here actually pause a moment and I hope I could read your mind what your answer is. So to give you a teaser, today's talk will not give one decisive answer to this question. I will instead give some the more intrinsic answers, intricate answers in two parts. My first part talk will say yes, it's easier in some sense. And my second part talk will say no, it's harder in some other sense. And the whole point of my talk is to convince you that I'm not self-contradicting myself. Okay. Before I dive into the technical details, let me make two disclaimers. I really like to make two disclaimers that came from my battle, my career's battle experience with reviews in CMT and Open Review. So two things I want to set an expectation first. First, I'm not gonna talk about or invent any new algorithm in today's talk. For most of it, I will only be talking about the most basic unstructured pruning, but I will change different views to look at this pruning algorithm. But we will always be looking at the simplest old textbook algorithm from the time of brain damage or optimal brain damage. Well, I tend to not invent any new algorithm until absolutely necessary, because of my own experience that many new algorithms are not necessarily outperforming the old. And we're talking about sparsity, so we respect or comes from that principle, right? Why we should invent one new algorithm unless we really have to? So no new algorithm today, just a bit of observations. And I will also be mainly talking about the unstructured sparsity, which many deep learning people, including some of my students, will despise as a toy kid sparsity, which is true in some sense because unstructured sparsity, which means remove by element without any pre-specified structure, is often not friendly for modern days GPU's acceleration. I will also mention some N over M experiment for the sanity of hardware people, but I like unstructured sparsity because I treat this as an analytical tool. Unstructured sparsity to me is the only way for me to continuously swipe the sparsity level if I wanted to observe the model performance with a wide spectrum of sparsity ratios. So I consider this as an analytical tool that I could continuously observe the phase transition of model behaviors if I really want a high resolution observation. And there are more reasons I like it. For example, unstructured sparsity is often more flexible and therefore better at preserving performance than structured sparsity, because structured sparsity will ask more structures of the weight besides just being sparse. And therefore, when we research unstructured sparsity and can research a certain performance level, it could often be considered as a performance empirical upper bound of what you could achieve with unstructured sparsity. So that's what I usually like to do. First, look at unstructured and then go structure. I like unstructured sparsity a lot in my research. So to the extent that I even wrote a handbook last year with my postdoc Shiwei. He's in Oxford now, we wrote an article together, and in one part of the article, we specifically wrote a long defense of unstructured sparsity formulated in this question, and in specifically answer to the review comment like this method is only demonstrate unstructured sparsity and herefore has no practical value. So trust us, you can see we are so mad because we got those same questions so many times from our papers. So we decided we would rather write a public response in a public article. The next time we get this same question, we'll just refer the reviewer. Please look at this online article, question 3.5, and that contains all the answers we prepare for you. That really worked. We did this once in last year's Neurons. So you're welcome to take a look at this article, and maybe next time if you want to write a rebuttal, you can directly make a reference to this article just for fun. Okay, so now let's dive into the technical part. Part one, as I promised, I want to make a case that compressing larger models is becoming easier. And the main part is in our last year newspaper titled The Emergence of Essential Sparsity, done with my student, the PhD student Ajay, and my postdoc Shiwei, and my then PhD student Tianlong. So both Shiwei and Tianlong are now faculty members now. Shiwei is in Oxford and Tianlong is in UNC Chapel Hill. They are both doing great works. All right, so let's start from something more classical, old-fashioned sparsity in deep networks. How would you, so the textbook level sparsity of old neural networks is gained from the following way. Start from random initialization. Let's train until convergence, get a trend neural network. And then looking at the trend weight, we could apply some importance criterion to decide the set of unimportant connections, which we believe we could remove for compactness. So we would remove those unimportant weights, resulting in a sparser topology based on those trend weight. And because we remove the weight, the performance may have dropped a bit. So we usually will follow with a retraining stage by fixing this topology and improve the performance as we can. And practically, we were iterative between the two steps of pruning and retraining until we reach a better, satisfactory trade-off between sparsity and performance. This is the textbook level iterative pruning and retraining, and that happens post the training. So a natural question people ask later was, well, the pruning this iterative post-training way would give us a lighter network for inference. But it does sound like to post more in training stage. Actually, you need to train the same network multiple times compared to dense training just one time. So that makes your training stage more expensive. Can we claim the benefit of sparsity during the training stage, doing something like pruning the network at initialization and just directly train this prune the sparse network? That would be nice because I would be able to enjoy sparsity throughout the expensive training process. But in the general case, this is not that feasible because of the famous conclusion that sparse neural network has a more ill-posed top landscape. Well, this is one nice photo I get from Tom Goldenstein's paper in 2017, where he shows that after pruning, the original network landscape become more rugged and therefore more unfriendly for gradient descent to explore. So training from scratch is generally harder after sparsity. However, the story is a little bit different if we start from a pre-trained model. We have done a study, done study back in 20 and 21 by leveraging the concept called lottery tickets. So lottery tickets is defined as one neural network, special sparse network that can be found from the scratch and found from scratch and trained isolatedly to match the performance of the dense network. So it would be this ideal sparse network that you want to look for at the beginning. One caveat of that, though, is what typical lottery tickets need to be found by iterative retraining over the same initialization. So in order to find a lottery tickets, you need to already pay an expensive pre-training cost using the algorithm known as iterative magnitude pruning. But we were able to demonstrate that if you do the lottery tickets over the pre-trained model, then here means, for example, in computer vision, we could train this we could do iterative pruning and retraining on the pre-training stage. Here, the pre-training may be done by contrastive learning or mask autoencoder, and we do we pre-train and prune by the simplest criteria magnitude and iterate between the two. This will sound expensive for sure, but the benefit of doing that in pre-training stage is after you do this iterative pre-train and prune, the resultant sparse pre-trained model is the same transferable as the dense pre-trained model. That means that you could directly use the sparse weight to be downstream transferred to all the downstream tasks while maintaining the same level of performance across tasks. So that will be a reusable sparse network. Therefore, although the iterative pruning and pre-training cost more than a one-shot pre-training, the extra pre-training cost would be able to be amortized if we reuse the same sparse mask in downstream. That's the point why you want to do the lottery tickets sparse mask finding on the pre-trained model. So we empirically demonstrated this idea to work profoundly on both NLP models, CV models, and later even multimodality models. That we can find a sparse pre-trained subnetwork on the pre-trained weight that is the same transferable. So our result on the BERT model that time was able to gain a good deal of media attention, including MIT News. So that was a background. However, now we are escalating the case from the BERT level to what we now know as a llama level. I still remember by the time when we do BERT experiment in 2020, that burns my whole summer of GPU farm to do iterative retraining on BERT, especially BERT-based. That was called very expensive. But the cost of pre-training BERT would would be called nothing if we compare with the true cost if I want to pre-train Llama and Vicura, right? And if we're saying, okay, I want to do iterative pruning and retraining on Llama Vicua, I'm not even talking about the GPT-4. What I'm talking about, right? No one, or at least me as a GPU pool academic, wouldn't be able to afford the cost to extend this idea. Iterative pruning and retraining on pre-training stage, I wouldn't be able to extend this idea to nowadays large language models or other foundation models. So the question we want to ask is, any chance we could simplify this idea of iterative magnitude pruning, IMP, at the pre-training stage? And that's why we turn to study the concept of essential sparsity as a rescue.
Could I ask you a very quick question? Sorry, it might be a stupid one, so I might have missed something. But on the previous slide, when you do so, you train the dense model, and then you prune the ones that have the smallest magnitude. And then on the next iteration, do you just continue training from where it was left off? Or do you reset the weights back to the original?
No, I never reset the weight. Once the weight,
okay.
No. Okay, so depending on what you mean. Once the weight becomes 0, I will never. It will be frozen.
Yeah, sure.
Yeah, if it's
but the rest of the weights continue from where they were before.
Yeah, it's a typical lottery ticket fighting scenario, which means all non-zero weight after this round of training will be reset to either random initialization or early value, which is
that's what I thought. Okay.
Yeah.
Got it.
Okay.
And then at the end, so it's not like you continue training from where it was left off. You kind of reset them back to random initialization or what it was before. And the idea is at the end, you have this sparse network which is retrainable from random initialization, and it's still
that is correct. That's the default principle of.
And the point is that this singular sparse architecture. So it's actually about the architecture and not the values. So I guess the question, because is it about the values or is it about the architecture? Because if it's reset to random values, then it's about the architecture and not the values.
Well, it's about both. It's about both the sparse topology and their original random value. The
original random values.
The random value is initialized, but once you do sparse selection of the randomly initialized values, this set is minimal.
And they stay fixed.
And we use them in couple with the sparsity. They are coupled together. They're called a lottery ticket.
And the point being that actually this singular sparse architecture that has the sparse connections and also the values that is retrainable from scratch, this exact same architecture can be trained to do different tasks. Is that the point?
It's well, in the classical lottery tickets, this finding process is usually done in one data set and one for example, image classification. Therefore, there's no reusability. And our point here is once you do the same routine on pre-trained model, you gain reusability. And this is a critical point to get rid of the extra overhead caused by iterative pruning and make the lottery tickets practical.
But when you say, okay, that makes sense. Yeah, I got it. Okay, thanks for explaining.
Thank you. Okay, so but even this cost can be amortized in pre-trained model. We don't want to pay the cost anymore when we come to Llama level. So we will define it. So we look at the essential sparsity as a rescue. Here is the mathematical definition I put in the paper. But if you hate reading notations, don't worry. I have the human language version for you. So in plain words, we define essential sparsity as the following special sparsity ratio range. Okay, so the dense model is called a sparsity ratio 0. And so this range, it has the following 2 defined characteristics. So within this sparsity range, firstly, within this sparsity range, if we use a one-shot pruning without training, which means we will just remove sparse magnitude, element with the smallest magnitude, without anything, just sort the magnitude and remove the smallest ones. This is called one-shot pruning without retraining. And just remove them. That can preserve the same performance as the dense unpruned neural network. Just so, in other words, those smallest pre-trained weight could be removed totally for free. You pay no price. And this should perform as well as any other fancy post-training pruning, including lottery tickets. So that's there. We hypothesize there's a range of sparsity you could claim that. And what will happen beyond this sparsity range? We further assume there is a sharp dropping point that can be observed once the sparsity growing beyond that range. After that, the fine-tuning performance of the sparse model After the above described one-shot pruning, will start to decline drastically, much faster as the sparsity increase. So it's defined as a saturation stage where sparsity hardly heard and a quick dropping stage. There is a phase transition in this essential, and this essential sparsity means the range of sparsity and the range of sparsity beyond which you will see the second stage. That's our definition. Okay. We will use many experiments to support the definition is empirically holding true. So we find that in general, essential sparsity is a widely observable inductive bias of sparsity in large language models and also pre-trained VITs. Significant portions of the pre-trained weight can be removed in a data-free and a training-free way. Data-free here means, but I think both here, but data-free means I don't need to use Allen calibration data or downstream data to specialize the removal of the weight. The weight could be removed based on just their pre-trained magnitude. And I don't need to do any domain calibration of that, just remove by magnitude. Training-free means either before the removal or after the removal. I don't do any extra training. I will directly use the remaining sparse mask and the remaining set of the pre-trained weight after such magnitude-based removal. There is no retraining. So it's completely for free. All you need to do here is to do a sorting, pre-sorting of the pre-trained weight. Remove the lowest top K% in smallest magnitude. That's all you need to do called pruning. So two remarks here. First one is, well, no, the one-shot magnitude pruning is practically very attractive to generate a sparse mask because number one, it requires no additional training, and the mask you can find is therefore identical and agnostic to different downstream applications. You don't have to store a large number of masks, just probably one mask, and no retraining needed. And remark two is, if for some reason you wanted to speak a trade-off between sparsity and performance, you could store, yes, multiple masks at different sparsity ratios. However, because because of one-shot pruning rank the remove element by the ranking of their weight magnitude, the high sparsity mask is naturally nested with a low sparsity mask. So they are all nested within each other in a sequence, as long as they're pruned from the same pre-trained checkpoint. So essentially, we can easily achieve trivial once-for-all sparsity without overhead of storing multiple masks. Though the effectiveness of one-shot pruning using magnitude has been similarly explored by a concurrent work called WANDA, a simple and effective pruning of large language model. I believe they got accepted just recently in ICLR 2024. And they also show that pre-trained weight itself is a strong indicator of pruning, although they use activation value to reweight the weight magnitude. Here we will use solely weight magnitude, the simplest. Okay, without house cleaning now,
quick question: what kind of proportion are we talking? Like in the case of Llama 2 or something, when you say a significant portion of the weights can be simply removed by weight magnitude, like is this like 20%, 30%? What's the ballpark figure?
Anywhere between 30 and 50%. I will dive into experiment for that.
Okay.
Yeah. Yes. It's very hard to go beyond the 50% for any large language pruning method at this point. 50% is almost a dead or alive point. Although we recently have a work called outlier weighted layer pruning, OWL. It's done by so that work can go to 70%, and is probably the only one I know that can go to 70% up to this point. But that was the key recipe of that is to do layer-wise sensitivity analysis and prove some layers heavier. But all the other methods, which assume uniform layer-wise pruning ratio, can go 50% as an empirical upper bound.
Okay, and quickly with the remark too, basically the point being that when you want to do high levels of sparsity, it ends up being the same weights and more. So kind of if you do a high sparsity, it's going to be the same mask as the low sparsity, just with a few extra additions. And therefore you don't need to keep storing the same index multiple times, and it's kind of nested. Is this the remark?
Yeah, that's a remark too, and that is a kind of special for for OMP, because for other methods they use other important criterions that is data dependent. So it cannot have nested property.
Okay, makes sense.
Yeah, so this is just some beauty of simplicity we enjoy here. So now let's dive into experiment. I started my experiment with OPTs because they're more manageable. I promise you I will show you Llama and BigQuery result later, but now let's look at the OPT and also include the bird base. The first thing we observe is this trend. So for all those figures, you will see different colors meaning different models, and we do the different meaning different models, and each of the figure is one of the downstream tasks. And but all those models here are tested in the same pre-trained checkpoint, pruned using OMP, one-shot magnitude pruning we just described, and x-axis is the sparsity we look at. Okay, so we use a different downstream task performance to understand the performance implication of the pre-trained pruning. As you can see, so the trend here is pretty consistent across different downstream tasks in squad and in glue and squad. You can see most of them following the same trend. The performance will first saturate in the same plateau for a while as the sparsity goes a bit heavier, and this saturator can usually last until you can see the curves 40%, 50%, usually within this range. Some tasks you will see the performance be more sensitive, like in this one. RTE task, you can see the performance. Some of the models, the smallest bird will start to drop performance earlier, and OPT models will drop later, but between 30% and the largest one will start to drop performance in 40%. Oh, sorry, this one is not the smallest bird. It's the smallest OPT will drop earlier. So is there some task will start to drop performance earlier? That depends on the task difficulty, downstream difficulty. There were some will be affected earlier, but most other tasks are consistently affected, not affected until the range of 40% and 50%. That's pretty consistent. One interesting niche observation I want to make a mention here is though, we can find there also exists a range when you apply the sparsity, the performance, the downstream performance improve a little bit compared to the dense pre-trained model in other than decrease. So you can see the range is usually much smaller. For example, in most tasks, we can often usually say 10 to 20%, and beyond 20%, some task performance already start to drop. But there exists a very small minor sparsity range where even you don't have much efficiency gain, you have a little bit of performance gain. And this, for people who do sparsity, may not cause much of a surprise as well. Because as we actually have a prior work on this, we find that in most of the downstream tasks, where the target domain data is considered as small compared to the source domain, sparsity itself could apply as a effective regularizer of learning without forgetting to avoid overfitting the target domain. That is also why sometimes when you apply other PEFT and parameter efficient tuning method on few shot transfer, the performance is even better than naive fine tuning because it does not change the pre-trained weight too fast. So that's the same flavor of the observation here. Some small sparsity can even boost the performance, but in the general sparsity range up to the 40-50, we will mostly claim they maintain the performance. But after this turning point of 40 to 50 sparsity range, you will see the performance start to catastrophically drop until eventually to the trivial level. Okay, so that's on the language model. Yes.
Very quick question. What does the scoring mean exactly then? So kind of -12, it goes down to at the bottom, and I see that the red line is drawn on -1 for all of them. What does that score axis mean exactly?
Oh, it's okay. So that's the score. I don't think we have unified the mostly accuracy, and the accuracy here I believe we're just using percentage dropped from the original dense sparsity.
Oh, percentage drop. Okay.
Yeah, the percentage. Yeah. Okay.
That's even at 90, it's only 10% worse. So it's still. I mean, I say that only. That's
oh, sorry. I want to correct myself. I don't think we use percentage here. I think this is the absolute number.
Okay, and it's just on some score ratio. It'd be interesting to know what that means in terms of like percentage. I mean, I guess with language models, it depends.
Yeah, I don't think it's. I need to check it back. I forgot the detail of the experiment, but I don't think it's. I don't think it's a percentage because the two,
Okay.
it's a
It would be too good.
It would
Yeah.
too good to be true. And also those
Yeah,
metrics are different. There are F1 and accuracy. Sorry.
Okay.
Yeah, I need
Yeah,
to
no
check.
worries.
I believe those are some absolute numbers though.
Sure. Okay.
Okay. All right. Sorry about that. So the and we even and so but one more thing we have noticed is this so-called essential sparsity, while empirically is consistent among a large range of tasks, is affected by downstream task difficulty indeed. There exist difficult tasks where the essential sparsity will be lower, the turning point, which is understandable. So we further verify the essential this dropping point behavior at a different difficult level of arithmetic reasoning data set, where we could take tasks from the grade 3, grade 6, and grade 9 exams. And we do find when the tasks become difficult, the performance drop comes easier earlier, should be understandable. And the second part of the talk will have a deeper dive into this phenomenon. And similar observations we have verified on vision tasks. So we have tried VIT base and VIT large, and we also on vision task we additionally conduct experiment of the same model, same data set, but trained using supervised classification objective versus self-supervised DNO perspective objective. One interesting observation we found of vision is self-supervised objective here seem to be more sparsity inducing compared to supervised objective. That is, DNO models seem to be able to tolerate a higher level of one-shot sparsity than supervised models. So that is a bit counterintuitive too, because we always thought the self-supervised models contain rich features. But here we have another explanation, that is sparsity may be an indicator of feature being more structured and therefore informed. So we can also say self-supervised learning learned more structured features compared to supervised learning, which may be overfitting one task. So downstream generability itself may lead to feature structure and more sparsity friendly. So that's something we observed here. Oh, this is okay. So although the experiment come from observing the already trained pre-trained point, here I didn't do any pre-training. I just download the checkpoint and do pruning and will observe the downstream performance. The next question we want to ask is, how this essential sparsity phenomenon emerge from the pre-training dynamics? So to do that, my student did some really expensive experiment to retraining the BERT base from scratch at different settings. And we mainly look at we mainly look at the relationship of the training epochs when we early stop training at different iterations and the training with different data volumes. So this all experiments here are done on BERT base. Oh, the first thing you can observe here is when we try on the leftmost figure, we have a trained model and with different pre-training data volume. So we use the full pre-trained data set of BERT 100% and gradually downsample it up to 60%. There is one very interesting phenomenon. So we find that when you train with more data, starting from 100% pre-trained data, the BERT-based training will see a very clear sparsity boost. Here, sparsity is defined using a threshold values. Threshold values. So lower than the threshold, the small value is counted as 0, and we count the total number of zeros in the pre-trained weight. So we can find that once we use the full training set, there exists a sparsity turning point at the early pre-training stage. After that, the sparsity drastically increased. So there is a phase transition during the pre-training dynamics. And but as we reduce the data more and more, the phase transition becomes more and more unclear. And when you use only near half of the pre-training data, there is almost no phase transition, and there is no sparsity induced from the pre-training dynamics. So this again, this may look counterintuitive again from the first glance, because why I should be more sparse once I train with more and more data, right? But I tend to understand using the same intuition between this one and the early one, why self-supervised learning lead to higher sparsity. That is, more data and self-supervision both will lead to more structured features. And here we say the features may have, and the more structured features will have more self-condensation and forming into more compact structures, which actually means they are more informative compared to the unstructured features. So this is we call this knowledge condensation. And once we have more data during the pre-training will lead to higher sparsity in the learned features. This is initially counterintuitive, but later constantly verified observation we found. And we also observe the same phenomenon to be consistent with the downstream performance we could have achieved. So so a summary we could make up to this point. We can, from the experiment we show so far, we find essential sparsity as indicated by the sharp tuning point of performance in downstream task performance is widely existent. While it is a little bit downstream task dependent, and how the actual ratio will reside depending on the task complexity, the sharp tuning behavior is universally observable. Self-supervised learning seems to generate more specifiable features. And we also observe the phenomenon on last page, which we call abrupt specification. There is a sudden emergence of high sparsity during the pre-training stage of BERT models, and the higher data size will make it easier to occur. And we should call this two-stage behavior in pre-training when the data size is large enough as knowledge condensation, assuming that large enough data will cause the feature to form a stronger structure manifested in the form of sparsity. In fact, I'm not too surprised. Is there a question?
No, so I was just going to quickly say, sorry, when this is the zero weight count, is this the number of weights that was zero at the point at which it crossed the essential matrix line on the graph?
We use a threshold. I believe in experiment we use a threshold of 10 power minus 5. So all weight slower than that is counted as 0.
Oh, I understand. Okay, fine. So it's the number of weights that actually end up going towards 0 during training.
Yes. At each stage, we spot a lot of checkpoint and plot this curve.
Yeah, okay. Makes sense.
Yeah. All right. Okay. Well, yeah, and in fact, I myself was not very surprised when I seen this tuning point behavior because it has been observed in our earlier work before at an even smaller scale experiment. We have an earlier paper in ICLR 20 called Early Bird Lottery Tickets, where we verified in vision model training, there also exists a earlier checked time point, roughly 15 to 20% of total training epochs. After that epoch, the sparsity level is significant. That there exists a time period of time during training where the sparsity suddenly jump. And after that point, the sparsity level become roughly constant and the sparse structure become constant as well, which means which weight is more important, which level is less important is roughly decided at the relatively early time point of training. So we have observed the two-stage sparsity dynamics in training, but now we are observing it again in the larger scale model pre-training. There is a tuning point behavior. So that's a main message from this part of the figures. So now let's continue and go to the experiment I promised you. Let's go to the billion level stuff. We have conducted the essential sparsity experiment on VCUA 7B and
sorry to interrupt. There's a couple of questions on the YouTube video. So
please.
The first one is there any estimate on the functional relation between the total number of parameters and the number of parameters you can remove with sparsity?
Okay, we don't have a predictor function accurately, but we have some ballpark numbers. In around the billion level, we can usually safely remove between the number we will recommend is between 40 and 50%. I would by default choose 45%. That's for billion level. When I deal with half billion, 1 billion, probably even 3 billion, that's where I would do. Yeah. And on this 7 billion and 16 billion level model, as I was about to introduce, we can observe the removable range to be smaller on those bigger models. In fact, that shows those bigger model has indeed learned more stuff compared to the smaller models. The sparsity range ratio here, the ballpark number is 30 to 35%. And within this range, as you can see, all on the downstream task, OMP without retraining performs just as well as the most expensive pruning method recently announced called Sparsity. It's a second order pruning method and costs more time. But yeah. But I do like to make a comment here, though. So essential sparsity only declares the performance within this sparsity range. So if you don't only count sparsity within this range, then all pruning methods almost all perform the same. There's no reason for you to pay extra. However, if you care about the performance beyond this range, we do acknowledge that better pruning methods are still meaningful if you want to chase higher sparsity. For example, we observe on Vicua that sparse GPT can still perform much better within the range of 55% to 65%, where it outperforms other pruning methods and definitely outperforms this simplest OMP. However, again, all methods we tested here perform comparably bad when sparsity is higher than 70%, especially at this level of 7 billion to 16 billion. If you care about 60 billion, 70 billion models, you are able to remove more than 70%. But in the most popular range, 70% basically will fail most published pruning method, except for one, which we just discussed, the OWR method done by my postdoc Shiwei. Yeah, so this is the three-stage picture of pruning method comparison. Within the sparsity range on the lower end, every pruning method is the same good. There exists a moderate pruning range, where good pruning method is better than bad pruning method. But there also on the high sparsity range, all pruning methods become comparably bad. So that's the whole picture of pruning.
Yep, thanks. Hope that answers the question. And the next one was, so the higher the data volume, the more the zero count features. That is, we can save on compute if we prune it to 60-70% initially without losing much in performance.
Sorry, is this a question?
Yeah. So yeah, basically it seems to be a question. So higher the data volume, more the zero count features. We can save on compute if we prune it to 60-70% initially without losing much on performance.
That is a result we only observe. Okay, so this result is only done on BERT base. I don't have the budget to retrain llama from scratch at different portions of pre-training data set. So I wouldn't claim this is necessarily true on llama level, but this is true on BERT base level. More data will lead to more prunable model. But we do have some experiment working from our work in progress though. We find that if we continue training the llama checkpoint using some sparsity as well, continue pre-training recipe, we can make a llama more prunable. So we can achieve eventually 70% sparsity or even higher. So you can pre-train the model better to make it more prunable. That's the right message.
Yep, thanks.
Thank you.
Thanks a lot.
Okay. One last thing to comfort the hardware carrying people is we also test essential sparsity on structured 2/4 sparsity pattern. And here's the result on OPT 350 million on the most popular 2/4 sparsity. And we can also observe that in the 2/4 sparsity range. So the metric here are both accuracy. So here on the left are both sparsity as accuracy improvement or decrease decrease at the different sparsity levels. To clarify, here we measure the performance drop. So if you see the okay, so if you see if you see a positive value, that means the performance is not dropped; it's even increased. But if you see those values on the negative direction, that means the performance dropped. So which means okay, so on the most popular 50% sparsity 2/4, the performance will be dropping, and sometimes to a large extent. And on the right, we also compare on the 2/4 sparsity using our magnitude-based way versus a sparse GPT way. Here, magnitude-based N/M sparsity means I will just compute the group-based total magnitude and remove the groups and remove element based on the groups. So 2/4 means every 4 element I will remove 2 and I will just rank magnitude within this group. So same trivial extension. So compare with compare with the dense model, our method will lose some performance on the N/M sparsity more than it will see unstructured, understandably. However, the point we want to make here is the performance you can achieve with the more expensive sparse GPT is roughly on the same level compared to what we do. Both will lose performance. So while in N/M sparsity, we cannot match the dense model performance, it does seem that we roughly match the performance of sparse GPT on this very specific case in semi-structured sparsity. Overall, I should say that the sparse GPT is a much more robust method on different settings, but in many of the experiments we do, we also observe the performance could be approached by much simpler method. While in higher sparsity, sometimes you still want to try this method. It's in general very robust. So far, my de facto choice if I want to prove model myself. All right, so that concludes my first part of talk. And if there is no further question about the first part, I want to go to my second part. Should I proceed?
I think so. I got a couple, but I can save them to the end, I think. Oh, well, and maybe just a quick one.
Yeah, sorry.
Also, I was going to say quickly, Atlas, on our side, we can go over a bit. I don't know if you have a very hard stop in 15. We can overshoot a little bit if you can as well. Do you have a hard stop, Atlas?
I think I can stop. I might need to stop at 8, so we have 12 minutes to go.
Okay. Well, maybe let's save questions to the end. I'd suggest let's do some questions at the end.
Yeah, but the second part is relatively quicker. It's even more straightforward message. Yeah.
Okay.
All right.
Sounds good.
So the second part I want to convey a conflicting message though. Similarly conflict that larger models may be harder to compress, but that's from a different viewpoint. Also, this connects to the one message we convey from the first part. That is, the essential sparsity one model may tolerate is dependent on the downstream task. So harder to compress, here the harder to compress also arises from what tasks to choose. And this was described in our paper of iClear 2023 called Sparsity May Cry. It's a benchmark effort. We do this, so we create a benchmark because we are so tired of people reporting pruning method on ImageNet classification mostly. Sometimes we even see results on CIFAR and MNIST, which I really don't read any useful information from there. But we spend some time to curate a much larger pruning benchmark using that dataset and models at unprecedented scales, and also at novel tasks that was not much tested before, including common sense reasoning, arithmetic reasoning from language models, protein stability prediction from AlphaGo style by protein foundation models, and also multilingual translation models. All come the large and base level models at a billion level. For example, with the bird base we use, the bird models we use here, robotic, is double sized over bird base and robotic base. It has 12 transformer layers, and the 12 transformer layers, 6,000-ish dimensional feed-forward network, and 12 attention head. Transformer XL we used here, we have 4 layers and 256 dimension encoding layers, 8,000-ish dimension feed-forward network, and 8 attention head. So basically, each of the tasks are new, and we choose basically the biggest model we could find on each of the tasks. So pruning them are also burning my GPUs a lot throughout the summer, but thankfully we're able to make it. And based on this benchmark, we have thoroughly tested the popular standard pruning options, including pre-training, such as lottery tickets. We indeed try lottery tickets on those, so that's a lot of iterative retraining, magnitude and iterative retraining, and random pruning. So we also tried during training, graduate magnitude pruning, and prior training, pruning before initialization method, such as SNP and other random methods. So the main message is very simple. I wouldn't bother you reading all those figures here. I will jump to the message here to take home. You can always check the result from our paper. Number one message is Well, fortunately or unfortunately, almost all the SOTA pruning method bluntly fail on those new and scale-up benchmark method. Failure here defined as on all of tasks using current pruning method, the performance will drop at a relatively trivial sparsity range. Relatively trivial is means 30%, 20%, and sometimes we are even able to find the pruning start to fail at a sparsity between 5 to 10% of sparsity. So that's basic means that they are unprunable. So that further confirms the message we inspired from the prior work. Whether pruning is easy or hard is not just a model dependency. In the foundation model age, where downstream performance becomes the golden standard, it also heavily depends on what the downstream task we are looking at. And the much more sophisticated logical reasoning-based downstream task will be way more fragile compared to perplexity or other simple glue or squad level metrics. We also have some additional insights. For example, we find number one, model of prunability is intimately related to task difficulty. We could design task difficulty levels to vary within a range, and we find that as we continuously increase the task difficulty, pruning becomes more and more difficult, and the dropping point comes earlier and earlier. We also find that in this, when the task is difficult enough, the success of pruning before initialization is hard to generalize. Pruning before and during initialization has been widely studied in sparsity literature because, as I teased earlier, if you could prune model before training, then that's the best efficient training you could expect. And there are a few methods such as SNP, GRASP, or SynFlow that shows success up to CIFA and ImageNet level when you prune an image classification model. However, we find that success hardly generalized when the model becomes larger and the task becomes difficult. We did not find a statistical difference between their performance and any random pruning before initialization. So that solves pruning before initialization is still a basically unsolved problem at a scale. The third observation is the iterative magnitude pruning, the de facto method we look at. I mean, here I mean iterative and pruning after retraining, also does not generalize much better compared to the one-shot pruning method without even without retraining. So there is no clear advantage when the model is very complicated, whether you prune and retrain multiple times and one times. That is different from the iterative benefit we always observe at a ResNet scale. And the last thing we find is from all the pruning methods we have observed, which are basically utilizing magnitude or gradient-based information, we find that they converge to extremely similar layer-wise sparsity ratio distribution. And so that leads us to conjecture that layer-wise sparsity ratio might be another breaking point if you want a better pruning method. Indeed, we are able to dig this out, and that's in the work I mentioned, the OWR, that's a paper I really like. So we conjecture that if pruning method in the large models, layer-wise sparsity ratio is a very critical parameter. And if pruning and all pruning methods converge to similar layer-wise sparsity ratio, may have similar performance. That's our conjecture. And reverse conjecture from that is if you could improve the layer-wise sparsity ratio, could improve the performance. That was partially validated by the other OWR work. But in this benchmark, because we only look at all the magnitude and gradient, all look similar. But we later do the experiment and try second-order pruning method, such as SparsGPT. And indeed, second-order pruning seem to converge to a different layer-wise sparsity distribution. And that also performed better. So that's another interesting to keep in mind. So that's, as I said, a second part of information, as I promised you, they're straightforward. But before I end my talk, I want to conclude what I'm saying today and make sure the right messages are heard without confusion. Am I conflicting myself? I hope I have convinced you that I'm not. So the message of this talk is sparsity in a larger pre-trained models is easier in one sense. That is, expansive pruning may no longer be that necessary compared to the simplest options. Magnitude-based heuristic seem to be an unreasonably strong baseline and a shortcut. And that tells us that when the model becomes really large, the parameter space seems to have a high redundancy. This is known to us. But this high redundancy also becomes more easily separable by simple signals as simple as the weight magnitude. You can use weight magnitude to separate important and unimportant parameters to an extent, and within that extent is almost as effective as other more expensive signals. So this is an unknown message before I do experiments. But in the meanwhile, this specification is also harder in another sense. That is, if you care about the model performance in those most challenging downstream tasks, then you will find your pre-trained models very fragile to high sparsity. And this is an inevitable issue that one must concern about, because pre-trained models, now we care about their difficult task performance. That's where we push a boundary, right? And when the latest language models are able to multitasking, zero-shot generalization, do in-context learning, we must care how their performance are affected by sparsity. In fact, in one of our latest work accepted by ICLR 2024 called Compressing LLMs, the truth is rarely true and never rarely pure and never simple. We show that pruning has a more complicated message when you care about zero-shot and in-context learning performance. You can check our paper; it's on arXiv. So that shows that evaluation is more intricate than level, and it's become harder and harder to answer the questions such as what is good compression? How sparse is good enough? It becomes dependent on not just the model data, but also the task. So we also have recent work advocate a task-centric view of pruning rather than once-for-all pruning. Adaptive sparsity seems to be the way to go. And in contrast of the positive message, I also want to give a negative message that what I'm not concluding today, so I'm not wrongly quoted for what I talked about. Did I say pruning is a solved problem in large language models? I believe I was asked this from our news reviews. No, I didn't say that. Even I say one-shot magnitude pruning is more effective than we thought. The claim is made in a limited context. I just say it seems the pruning seems easier or can be simplified when in the essential sparsity range. I never say pruning is a solved problem in a high sparsity range. We ourselves are continuing exploring the high sparsity range over 70%. I think that's still a very meaningful research area. And pruning is certainly become only harder if you care about the versatile and difficult downstream task generalization. So no, pruning is not a solved problem. And did I say magnitude pruning is the best pruning? No, I didn't say that. I only said it's as good as the unpruned dense model, but just within the essential sparsity range. As I keep emphasizing, other respectable works, such as SparseGPT, which utilize a second-order pruning method, may work better at higher sparsity range and may work better at larger models. However, this number one may or may not be relevant if you really care about the undamaged performance from the dense. So if you're really religious, the performance cannot drop at all from the dense model. You probably cannot go very far yet in the high sparsity range. And in the current favorite parameter range, we call 7 billion and its neighbors. It's pruning without performance damage is still very hard. Of course, the pruning without damage is much easier if you go to 70 billion or much larger because the parameter is necessarily redundant. But I think practitioners not like 3 billion, 7 billion, and 13 billion is the best. And within this range, pruning without damage is very hard. And also in the more restrictive N over M pruning sparsity, we see little evidence that any pruning method performs better than the others. N over M sparsity is just the same difficult as everybody. And did I say that all pruning methods will fail at harder downstream tasks? No, I also didn't say that. We verified a range of tasks on range of pruning options on our benchmark called Sparsity May Cry, SMC. But that's only the range we tested. Later, as we also acknowledged, we tested later the second order pruning method, such as OBERT and SparseGPT. They are able to survive higher sparsity range better than the first order method, but they also see some performance drop, although milder. And one last thing we care with, one thing we find very notably is compared to what pruning method you use, how you do retraining, the recipe of training hyperparameters in many times matters much more than what pruning method is you are using. How to tune the learning rate, how many epochs you should pre-train. Do you use hard labels or soft labels? Where you should rewind the weight. Should you use continue train on the prune the weight, or you should rewind to the very beginning or somewhere in the middle? All those play a very important role on the pruning method, on the pruning pruning performance recovery. So these are the really hidden heroes on the best pruning method we care about, not the pruning fancy algorithm themselves. So the overall message I want to take as a quote is developing cheaper yet more generalizable pruning method on large foundation models remains as an open challenge, but there is opportunity. We could go cheaper pruning. With that, I'm able to conclude my talk on time, and I would like to thank you for having me today again.
Amazing. Thank you so much, Alice. That was really, amazing talk. I guess everyone can give a round of applause virtually. We can do some clapping hands. Cool. So if we got some questions, I guess, Anwar, you had a question to kick us off?
Oh yeah, quick question. In addition to the qualitative analysis that you did, like for example, you measure a particular loss function with different sparsity ratios. Do you also do any kind of qualitative analysis? Like, do you actually measure the model performance? Like, do you actually run the model and see how the output is? Because in a lot of cases, I've read that it, even though there may be no effect on the accuracy, the compression may bring some artifacts. So, for example, with speech models, there may be some.
Absolutely amazing question. And I didn't have time to cover, but please check out ICLR 2024 paper, which exactly discussed this. The paper is called, I think I mentioned, Compressing LLMs. The truth is rarely pure and never simple. So there we present a benchmark called LLM Kick, short for knowledge intensive task, such as question answering, in-context retrieval, in-context summarization, instruction following, and we thoroughly evaluated, pruned, and quantized model performance on those tasks. I mean, actual performance, task performance, not just the perplexity and accuracy. And the same as your intuition, we find that the pruning will become way more sensitive if you care about the downstream performance. There are many cases where the perplexity still looks fine, but those downstream task performance still already start to drop catastrophically. So all those metrics reported here based on accuracy or perplexity is only a rough scale metric. The discussion could go much further if you care about the concrete task performance, and that paper should supply a more detailed answer.
Sure. Sounds good. Thank you so much.
Thank you.
I have a quick question, which is a bit open-ended, but how optimistic are you about the changing GPU landscape with the introduction of kind of sparse kernels and so on? And there's architectures like Grace Hopper from NVIDIA. There's more work, I guess, that's moving perhaps towards architectures that are a little bit more between the conventional GPU that's very good at dense operations and CPUs, where of course you can actually benefit from the sparsity because it's a little bit more dominated by the total arithmetic complexity.
Yeah,
I guess what hardware targets do you see as being the most promising to really showcase the benefits of sparsity, unstructured sparsity?
Yeah, amazing. I would say I'm very optimistic about the scope of GPU-CPU coexistence for utilizing large models. So unstructured sparsity is more promising on CPUs. And I think people, I don't know about my future, but I don't have a powerful GPU on the laptop I'm using right now. In fact, my group has been working on CPU-friendly sparse LM inference recently. And I know there are a few other amazing groups, such as Dan Lista in Neuromagic and people in Cerebras that have been diving into this a lot. And sparse GPU, and they are able to show structured sparsity plus quantization really gain latency benefit and while maintain performance better. And we also have recent work shows that we are able to run prune and quantize the Llama 7B on a not so good Windows laptop with a CPU occupancy range the ratio lower than 60%. So that means you online generate text while you still browse the internet and reply emails. That we have something in testing, being tested in-house. And I think in the future, as in people are generally interested in the range, as I said, 3 billion, 7 billion, or at most 17 billion. And if you prove and quantize on this level, those models can be comfortably fit into the memory of a normal laptop. So I think pruning will have the best hope there, focus on the offline and maybe CPU-friendly applications.
Yeah.
But I'm not saying that the GPU cannot utilize that, but probably in most for a while.
Yeah, makes sense. Sorry, I have just one more if you have the time on my side. Was just I didn't fully understand. So you're mentioning that structured features are more prune friendly in a way. So when you have more structured features in a network, it means that less of the weights need to be used in order to represent those features, and therefore the non-needed weights can tend towards zero. But I guess, can you give any more intuition on exactly what that means? So I guess in my mental model, a structured feature is one that is efficient with its use of the weights in a way.
I mean modularity.
Modularity. So the features are more modular, and there's like different groups of weights that are doing different like sub tasks. Is this kind of almost a way of thinking about it? And there's less wastage in terms of how those weights are being leveraged to do the tasks in a sensible way.
Conclusion is if you see enough data and enough tasks, the model will learn to decouple the neural functionalities. And the subset of weight will be responsible for a subset of knowledge. That's exactly the intuition when we started the mixture of experts, right? So if you only see one task, then there is no divide and conquer. When you see more data and more tasks, you are able to draw from the task dissimilarity, and the modularity will emerge during the pre-training. So modularity should be the right word here when I talk about the structure. Indeed, we actually have another work to show that when you train with more and more data, there are a mixture of experts like structure, even you train a dense transformer. So there are selective activation from different domain data and when you call different instructions.
But why does more modularity mean that a bigger percentage of the weights can be removed just because it's more organized and more efficient in the use of
more modularity means more modularity because all those essential sparsity
means more efficient.
All essential sparsity performance here is measured by downstream performance, and the modularity means in order to complete one specific downstream performance, I will only activate a modular, a subset, a dedicated subset of the weight, and therefore you sparsity.
Okay, so and then when one task
is compacted in one specialized of the weight. Information for another set is compacted in another subset.
I see what you're saying, because the accuracy drop is for one task. So in a way, all of these graphs are based on the performance on one particular data set. So you can then start to see that other parts of the other modules in the network are no longer needed, or not needed in order to perform well at this particular task. And that's why you have it, basically.
Yes, so here all the tasks are actually reusing the same sparse subnetwork.
I was going to say, because it's not based on, but it's based on the absolute magnitude of the weights. It's not based on the gradient of that task or anything. So
I agree, because on those figures, I can see the task tested is relatively simple. So we hypothesize that for those simple tasks, there would be the same backbone subset of weight doing all the same. But in fact, if you pay attention to the Sparsity May Cry paper, which shows that pruning will start to damage some more complicated tasks, even you start to touch at a very small weight, sometimes top 5%, top 20 to 50%. That already gives you an indirect evidence that some of the tasks will need those small weights be solved, and those small weight will be only relevant if you care about some specific task. This is already evidence of specialization. And one paper I didn't mention here, but would be interested to read if you care about the topic, is our more recent work called the junk DNA hypothesis. You can search on my Google Scholar. So that paper give more direct evidence there exists weight specialization when you care about the difficult tasks.
Okay, that will definitely give that a read. And when you say second order methods, that they're always conditioned on the input, I guess. So a second order method, is that based on the gradients observed when going through a particular task?
Second order method will use a pseudo hasten, and that need to be estimated by calibration dataset. So you will need a small data from pre-training for calibration.
But that makes it very hard, right? Second order methods for LLMs that's supposed to be able to do everything. How do you calibrate an LLM with a second order method when it's meant to be like an oracle that knows everything? I guess that's quite challenging, right?
Yes. Number one, so people like Dan has created a very clever estimation method to estimate the hasten. And number two, they empirically shows the calibration dataset size is relatively robust. You can use hundreds of examples from pre-training set, and the result is okay.
Yeah, okay, makes sense. I guess just with general large algorithm models, you need that data set to kind of represent all abilities than an LLM might be able to do. But I guess that's where the elegance of what you're showing really comes through, where it's literally just no data set, no gradients, no anything like this, and you can actually get pretty far.
Yeah. I think I love the simplicity of our method, but I should also applaud them because their empirical performances will have the gain. Like I said, there is a percentage of moderate sparsity where they still perform the most robustly.
Yeah, makes sense. Makes sense. I could ask a million questions, but I won't keep any long. There was numbers on the YouTube, I don't think, if I'm not mistaken. I think. Oh no, was there? No. Well, no. Just someone was asking how much do you think this is translate to current state of the art LLMs, but I think we then did get that answered with some of the later slides, which is. Well, that is very difficult. Basically, was the takeaway there. I think.
Yeah, well, I was about to say that if you check our more recent papers, we are almost exclusively working on LM pruning at the 7 billion and the 13 billion level, and many of the observations here are transferable. Well, just to check later archives.
Yeah. Okay. Well, we'll definitely check out the DNA junkie one as well, because that seems super interesting. Again, Atlas, it was amazing having you with us. Yeah, thank you so much for making the time. Again, let's give another round of applause with our virtual clapping hands. Again, yeah, thank you very much for joining us. Yeah, I hope you have a good rest of the day. I know it's a little bit earlier over in Texas now. I appreciate you making it early morning, getting up at 7, read a little bit earlier than I normally manage. Yeah, we'll obviously just stay in touch and maybe have you again on another reading group one day. But yeah, have a great rest of the day.
Thank you for having me. It's a nice way to start a day, though. And thank you for listening to my talk. Bye-bye. I hope you enjoy.
Thank you so much. Bye-bye. Bye-bye, everyone. Thank you.